In 1998, at an auction house in New York, a private collector paid $2 million for a small, badly damaged medieval prayer book. It was in wretched condition, moldy, charred at one corner, missing pages, with crude religious pictures painted over some of the leaves by a forger trying to raise the price. As a devotional manuscript, it was worth very little, but the parchment underneath the prayers was older than the prayers. In the 13th century, in a monastery somewhere in the eastern Mediterranean, a scribe had needed writing material and did what scribes did. He took an old book nobody was reading, scraped the ink off the pages, cut them down, turned them sideways, and wrote his prayers across the top. Parchment was expensive. Recycling was normal. The old book had been a 10th century copy of mathematical treatises in Greek, and the scraping was imperfect, under the prayers, ghostly and sideways, and half erased. The original text was still faintly there. Over the following decade, using ultraviolet light, X-rays from a particle accelerator, and computer imaging that could separate one layer of ink from another, a team of scholars read what was underneath. It included a work that had been lost for centuries, the only surviving copy in the world, in which the greatest mathematician of the ancient world explains, in his own voice, how he actually made his discoveries. Somebody washed off Archimedes to write a prayer book. It is the most perfect symbol of the fall of ancient science that anyone could invent, and it is not a symbol. It happened. He was born around 287 BCE in Syracuse, a wealthy Greek city on the eastern coast of Sicily, and he seems to have spent time studying in Alexandria, where Euclid's machine was still warm. Then he went home and stayed home, and for the next 50 years or so did mathematics at a level that nobody on earth would match again for 18 centuries. Of all the ancient mathematicians, Archimedes is the one who comes through to us as a person. Partly this is because he was famous in his own lifetime, for reasons that had nothing to do with mathematics. He was a celebrity engineer, the man who built impossible machines for the king. Partly it is because his letters survive, and he was funny in them. And partly it is because he died in a way that Rome could not stop talking about. Everyone knows one story about him, so let us deal with it first. King Hiero of Syracuse, the story goes, commissioned a gold crown and suspected the goldsmith of stealing, of mixing in cheaper silver and pocketing the difference. The crown weighed what it should. How do you catch him? Archimedes, stepping into a full bath and watching the water spill over the rim, realizes that a submerged object displaces its own volume, that silver is bulkier than gold for the same weight, and that a diluted crown will therefore push out more water than an honest one. He runs home naked through the streets shouting, "Eureka, I have found it." It is a wonderful story, told by a Roman architect 2 centuries later, and the physics of it is doubtful. Measuring the tiny difference in spilled water for a crown-sized object is right at the edge of what you could actually pull off with ancient equipment, and Archimedes had a far better method available, one he wrote up himself in his treatise on floating bodies. Hang the crown from one arm of a balance and an equal weight of pure gold from the other, then lower the whole thing into water. If the crown is adulterated, it is bulkier, so the water pushes up on it harder, and the balance tips. It is exquisitely sensitive. It uses the principle that actually bears his name, and it does not require anybody to run naked anywhere. I tell you the debunking not to spoil the fun, but because the real story is better, and it is the story of this whole chapter. The bath is famous because it is a story about a flash of luck, genius as a lightning strike, a gift from nowhere. What Archimedes actually left behind is the opposite, a record of the most disciplined, deliberate, and cunning thinking in the ancient world, by a man who was completely explicit about how he did it. He did not stumble into his results. He stalked them. Start with what made him famous in his own century. He could move things. The principle of the lever is the sort of fact that everyone knows and nobody thinks about. Put a weight near the pivot end pushed down far away from it, and you multiply your force. Any child on a seesaw discovers this. What Archimedes did was prove it, establish, from a small set of assumptions in the Euclidean style, the exact law relating weight and distance, and then push that law until it said something outrageous. If the law is exactly true, then there is no limit to it. Any weight, however monstrous, can be balanced by any force, however small, provided the small force is far enough out along the beam, which gave him the line that has followed him for 23 centuries. Give me a place to stand, and I will move the earth. Hiero, delighted and skeptical, is said to have asked for a demonstration on a slightly smaller scale. The versions differ: a ship dragged up out of the harbor, or a fully loaded vessel with its crew still aboard. But in every telling, Archimedes rigs a system of compound pulleys, sits down at some distance, and pulls the ship across the ground smoothly, hand over hand, alone, as though it were gliding through water. The crowd loses its mind. The king announces that from this day forward Archimedes is to be believed about everything. The engineering became legend when the Romans arrived. In 213 BCE, Syracuse having picked the wrong side in the war between Rome and Carthage, a Roman fleet under the general Marcellus laid siege to the city, expecting to take it quickly. It took 2 years, and the reason was one elderly mathematician. The Roman historians, writing for their own side, and therefore not inclined to flatter, describe the siege in tones close to horror. Catapults ranged to hit ships at any distance, so that as the fleet approached there was no safe interval. Cranes swinging out over the walls to drop rocks through the decks. And the machine they remembered most vividly. A great iron claw on a chain that would reach down, seize the prow of a ship, haul it up until the vessel stood on its stern, and then let go, dropping it into the water to swamp or capsize. Polybius says the Romans became so unnerved that if they saw so much as a rope or a piece of wood appear above the wall, they would turn and row away, shouting that Archimedes was aiming another engine at them. There is also the famous business of the burning mirrors, an array of polished shields focusing sunlight to set the Roman fleet alight. It appears only in much later sources, and every modern attempt to reproduce it has ranged from unconvincing to comic. It almost certainly did not happen. The claw, by contrast, is described by sober near contemporaries and is entirely buildable. Here is the part that matters. According to Plutarch, Archimedes regarded all of it, every machine, the whole catalog of devices that made him a legend, as beneath serious attention. Engineering was what he did when a king asked. It was applied, it was temporary, it was useful, and usefulness was not the point. He would not even write the machines up properly. What he wanted to be remembered for was the pure mathematics, the theorems, the proofs, the abstract results that would never move a ship or kill a Roman. We may raise an eyebrow at the snobbery, but do not miss what it tells us. This is a man who has understood, only 2 generations after Euclid, that the truths reachable by proof are of a different order from anything else a person can make, that a machine rots and a city falls, and a theorem does not. He turned out to be right, which is its own kind of terrible. So, the mathematics. And the mathematics is where he stops being a clever engineer and becomes something close to a time traveler. The Greeks, after the catastrophe of Chapter 3, had built their subject on geometry, on lines, shapes, and figures you could draw. That works beautifully for objects made of straight edges. Give a Greek geometer a triangle, and he will hand you its area without breaking stride. Give him a polygon of 97 sides, and he will chop it into triangles and do the same. Straight-edge shapes are, in a real sense, solved. Curves are not. A circle has no straight pieces to cut it into. Neither does a parabola or a sphere or a spiral. You cannot triangulate your way to the area inside a curve, because at every scale, however fine, the boundary is still bending. And so the great questions of Greek geometry were all about curves. How much area is inside the circle? How much surface wraps around this sphere? How much volume does it hold? There was a method for attacking these, invented before Archimedes and generally credited to Eudoxus, the man whose theory of proportion rescued Book 5. It is called the method of exhaustion, and the name is a little misleading, because you never actually exhaust anything. Here is the idea, and it is one of the loveliest in ancient mathematics. You want the area of a circle. You cannot get at it directly, so you sneak up on it from both sides. Draw a square inside the circle, touching it at 4 points. Its area is obviously less than the circle's. Draw a square outside, just containing it. Its area is obviously more. Now you have trapped the answer between 2 numbers you can actually compute. Then squeeze. Replace the squares with regular polygons of 8 sides, then 16, then 32. The inner polygon swells outward, hugging the curve more closely. The outer one shrinks inward. The gap between the two, where the true answer is hiding, narrows, and crucially, you can prove that by taking enough sides, you can make that gap smaller than any margin someone cares to name, however tiny. Then you finish with a contradiction in the classic Greek style. If the true area were bigger than your claimed value, you could squeeze the polygons in past it, which is absurd. If it were smaller, same absurdity in the other direction. Therefore, it is exactly your value. Notice what that achieves and what it carefully avoids. It gets an exact answer using infinitely many possible steps, but it never takes infinitely many steps. At no point does anyone say, and now let the number of sides be infinite. The Greeks did not permit that, and their caution was not stupidity. They had been badly frightened by infinity. Zeno's paradoxes, a couple of centuries earlier, had made a persuasive case that reasoning about infinite processes leads directly to nonsense, that an arrow in flight can be shown never to arrive, that Achilles can be proven unable to catch a tortoise. Aristotle had responded by drawing a hard line. You may speak of the potentially infinite, a process that can always be continued, but never of the actually infinite, a completed infinite thing. The infinite was to remain a direction, never a destination. Exhaustion respects that rule scrupulously. It is a technique for extracting exact answers about curves without ever once saying the forbidden word. And Archimedes used it to do things nobody would match until Newton. He proved that the area of a circle equals the area of a right triangle, whose height is the circle's radius, and whose base is its circumference, which is, in the clothing of Greek geometry, exactly the formula you learned in school. He established that the ratio of circumference to diameter, the number we call pi, lies between 3 and 10/71 and 3 and 1/7, a bracket tight enough for any practical purpose, obtained by working out the perimeters of inscribed and circumscribed polygons of 96 sides, by hand, in a number system with no decimals and no place value, computing square roots along the way. This is not a clever insight. This is labor, undertaken with total control, and the answer is correct. He measured the area under a parabola, a genuinely hard problem, the sort of thing calculus was later invented to handle, and found it to be exactly 4/3 of a certain inscribed triangle. That result has no business existing in 250 BCE. And then, his favorite. He proved that if you take a sphere and the smallest cylinder that will contain it, the sphere is exactly 2/3 of the cylinder, in volume and in surface area, the same clean fraction twice. It is an astonishing, unexpected, beautiful fact, relating a curved thing to a straight-sided one by a ratio a child could remember. Archimedes asked that a sphere and a cylinder be carved on his tomb, with that ratio inscribed beneath. More than a century after his death, a young Roman official arrived in Sicily, went looking for the grave, and was told by the locals that no such thing existed. He kept asking. Eventually, in a neglected corner outside one of the city gates, he found a small column nearly swallowed by brambles and thorn bushes, and had it cleared, and there was the sphere and the cylinder, weathered but legible. The Syracusans had forgotten where their most famous citizen was buried. The Roman who found him was Cicero, and he wrote it down, and that is why we know. Now to the palimpsest and the secret Archimedes kept. Read his treatises as they came down through the Middle Ages, and something is off. The proofs are impeccable, exhaustion, rigor, contradiction, everything airtight. But the results are uncanny. Where did he get the number 4/3? Exhaustion is a method for verifying an answer. You have to bring the answer with you. If you guess wrong, the method proves nothing. So how did a man in Syracuse arrive at exactly the right value for the area under a parabola before he began? For 2,000 years, nobody knew. Then, in 1906, a Danish scholar named Johann Ludwig Heiberg, following a footnote about a Constantinople manuscript with mathematics faintly visible under its prayers, went in, looked, and read what he could with a magnifying glass. What he found was a work called The Method, addressed by Archimedes to a colleague in Alexandria, and in it Archimedes does something no other ancient mathematician ever does. He explains how he really thinks, and it turns out he cheated. Not in the proofs. In the discovery. His private technique was to treat a geometric figure as though it were a physical object, a shape made of some material, with weight, and then to slice it into infinitely many parallel strips, each strip having no thickness at all, and to weigh them. He would imagine the strips of one figure hung from a lever, balanced against the strips of another whose area he already knew, and find the point of equilibrium. Balance the parabola against the triangle, read off the ratio, and there is your 4/3. Every part of this was forbidden. Figures do not have weight. A shape is not made of stuff. A region is not composed of infinitely many lines of zero thickness. That was precisely the kind of talk Aristotle had outlawed, and Zeno had made frightening. Archimedes knew it. He says so. He tells his correspondent frankly that this method does not prove anything, that it is a way of finding out what is true, so that afterward you can go back and construct a real proof by exhaustion. But that it is far easier to prove something once you already know it is so, which is one of the most honest sentences any mathematician has ever written, and it describes how the subject has actually worked ever since. Look at what he was doing, though. Slicing a region into infinitely many infinitesimally thin pieces and adding them up to get an area. That is integral calculus. Not a hint of it, not a foreshadowing, the actual central idea, being used correctly to get correct answers in the 3rd century BCE. 1900 years before Newton and Leibniz, a man in Sicily was summing infinitesimals. And he was doing it so well that in one passage of the method he compares 2 infinite collections of slices and matches them against one another, 1 to 1, in a way that edges up against the arithmetic of infinite quantities themselves. And he wrote it down as a guilty secret. A heuristic. A trick for finding answers to be hidden behind respectable proofs once the answer was in hand. This is the moment in part 1 that I find hardest to be calm about. The distance between where Archimedes stood and where calculus begins is not a vast conceptual gulf. It is one permission. He needed only to be allowed to say that the infinite sum is legitimate in itself, that a completed infinity of infinitely thin slices is a real mathematical object not a scaffolding to be kicked away. He had the machinery. He had the results. What he did not have, and what nobody in his world could have given him, was the right to use them in public. He was reaching for a light switch in a room that had not been wired yet, and the current would not be turned on for 19 centuries. There is one more thing he did, and I want to end on it, because it is the piece of Archimedes that speaks most directly to this book. He wrote a short work called The Sand Reckoner, addressed to King Gillen of Syracuse, and it opens with the observation that some people believe the number of grains of sand is infinite, that it cannot be counted, that no number could be large enough. Archimedes disagrees. And then, to prove it, he does something no Greek had done. He builds a new number system. The Greek numbering scheme ran out at a myriad 10,000, and a myriad myriads 100 million, was more or less the edge of the expressible world. So Archimedes took 100 million as a single unit built a second order of numbers on top of it. Then a third order on top of that. Then he kept going, constructing a scheme of orders and periods capable of naming numbers so large that writing one out in our notation would take 80,000 million digits. Then he asks how many grains of sand it would take to fill the entire universe. To answer, he needs the size of the universe, so he does astronomy. And in the course of it he reports, almost in passing, that a contemporary named Aristarchus of Samos had proposed that the sun stands still and the earth travels around it. That single remark in Archimedes is our best evidence that someone proposed heliocentrism 18 centuries before Copernicus. The book that survives to tell us is a book about counting sand. Being cautious, Archimedes takes the largest universe on offer, sizes his sand grains generously small, and grinds through the arithmetic. His answer is that the cosmos would hold fewer than 10 to the power of 63 grains, a number he can name comfortably, with room to spare, in a system he built for the occasion. Now hear what has just happened. Somebody said, that is infinite, it cannot be counted. And Archimedes said, no, it is merely very large, and infinite and very large are not the same thing, and I will prove it by naming a number bigger than the thing you called uncountable. He did not extend the number system. He invented a new one on purpose because the old one could not hold the thought he wanted to think. That is a move we are going to watch again and again for the rest of this book. The recognition that the numbers we have are not the numbers there are, and that when a question outgrows the available arithmetic, you build more arithmetic. 0 will be admitted this way. So will negatives and irrationals and the imaginary and eventually Cantor's transfinite numbers, which will do to actual infinity what the sand reckoner did to sand. Syracuse fell in 212 BCE, betrayed from within during a festival. Marcellus, who had spent 2 years being humiliated by one man's machines, gave orders that Archimedes was not to be harmed. The stories of what happened next disagree in their details. He was drawing figures in a tray of sand or in the dust of the floor. He told the soldier to wait until he had finished. He refused to leave until he had worked out his problem. He was carrying instruments the soldier mistook for something valuable. In every version, a Roman soldier who did not know or care who this old man was killed him. Where he sat, he was about 75. The line the tradition preserves, "Do not disturb my circles," is probably not authentic. It is too good, and the way the naked run through the streets is too good. But it survives because it captures something true, which is the only reason any of these stories survive. That here was a man for whom a diagram in the sand was more real and more urgent than an army in his house. Marcellus is said to have been genuinely distressed and to have arranged an honorable burial. Then Rome went on being Rome, and Syracuse became a province, and the tomb went under the brambles until Cicero pulled them off. And that is the end of part 1. Look back at the distance covered. It begins with somebody scratching a notch on a baboon's leg bone to remember something they were afraid of forgetting. It ends with a man calculating the number of grains of sand that would fill the universe, and a number system he built for the purpose, and slicing shapes into infinitely thin ribbons to weigh them on an imaginary balance. In between, 3 things happened that had never happened before. Number came loose from the things it counted. Somebody asked why, and the answer turned out to be a machine, proof that manufactures permanence. And that machine, almost as soon as it was switched on, produced its first monster. A length that no ratio could name, which broke the world that found it. The Greeks did something remarkable with that monster. They did not admit it as a number. They built around it, and their geometry first mathematics is the shape of that avoidance. But they also did not look away. They proved the thing, wrote it down, and left it standing in the middle of the road for whoever came next. Whoever came next would not be Greek. Because the story now leaves the Mediterranean, and the next several centuries of real progress happen in places that most histories of mathematics, written in Europe by Europeans, used to skip in a sentence. In China, mathematicians will be doing arithmetic with negative numbers, calmly and without fuss, 1,000 years before Europe stops calling them absurd. In India, someone will look at the empty column the Babylonians could never fill and give it a name, and rules, and a place among the numbers. In Baghdad, scholars will gather the mathematics of the entire known world into one library and invent from it a new way of thinking about the unknown, one that will hand us the words algebra and algorithm. The center of the mathematical world is about to move east and stay there for the better part of 1,000 years.